So this is how you add two vectors, right? And it's very easy to do. I'm not going to spend time on that. You have to understand it yourself, but I'm going to mention certain things. Like if I take two director line segments or vectors, right, then say I'm frequently switching from one type of representation to another, but you shouldn't get confused because AB is a vector, BC is a. Now I am looking at vectors as directed line segments. Okay. Now this is simply AC. Right. And this is in agreement with the parallelogram law, and this is in agreement with this way of defining it. Right. That is reflecting O about the midpoint. Okay. Now, when I good. Let me see. Now, I'm going to say observe vector addition defined as above is commutative. That is, A plus B equals B plus A. Do you see that? Say, how do I get the A plus B? The midpoint of AB. Midpoint of AB is same as midpoint of BAB. So M is the same. So reflect we get the same C. So you get that A plus B equals B plus A. Right? So the vector addition is commutative. Right. And then 2, vector addition is associative. What do we mean by that? A plus B plus C is same as A plus B plus C. Now, let's draw some simple diagram to check whether that's true. O, A, B, and then let me call this as C. Right. Now first I have to find A plus B. So how do I do that? So I have to look at the midpoint of this and then reflect O about it, right? This is A plus B. Is that right? And then what is A plus B plus C now? Here is A plus B, this is C. So I have to look at the midpoint of this, then reflect O about this. Reflect this is your solution must be the same, right? And this is A plus B plus C. Now if you had done the other way, B plus C first, right? I should have looked at the midpoint that we see, its reflection here, and then pick A. Now this is a simple geometry, so let me say for today it is an exercise. Right? Verify it geometrically. Verify. Right. Then you will see that you also learned a little bit of geometry as you recollect your geometry. Okay. But these are other ways of looking at it also. That is associativity. Right. But so for a moment, let's assume that we have verified it. Okay. Then 3. Consider the vector O when I say the vector A, what is that vector? OA. So if we call vector O, it should be OO, right? Direct line segment joining O to O. So it's just a point. So it is a degenerated line segment, right? Now this is a translation. See, a translation has two components, isn't it? One is a direction and the distance through which the point is moved. Now this is a translation which moves a point through zero distance. Through zero distance. Right. That means any point is moved to itself. It doesn't, right? Doesn't and this is the zero vector. Thus, A plus O. See, it doesn't move at all, isn't it? Yeah. So, here I have to take O, this is A, then the midpoint. What is the reflection of O about the midpoint M now?
Same.
A.
Oh, yeah.
So, we say that A plus 0 is 0 plus A equals A. So, of course, how do we define the addition? The vector O and vector A. Now, vector A and vector B, first I have to look at the midpoint. I have to look at the midpoint M and then reflect O about M. But when I reflect O about M, I get back A. So, this as a zero vector. So, just as integers, you can, so the addition and integers is commutative, vector addition is commutative, vector addition is associative. We have a nice zero vector. Right? So that any vector plus zero vector is the same as the same vector. So this is the identity. So you have a zero vector. So existence of zero vector is there. And then what is the other special property of integers that we saw? For every integer, there is a negative integer, m and minus m, so that m plus minus m gives you the 0, and which we call the additive inverse of the integer m. Let's see whether do we have a similar thing for vectors now. Right? Now, consider the vector A. So when I write consider the vector A, it means OA. Right? Now, where is the vector? Get me another vector so that when I add this, I get the zero vector. So what I can do is, say, I have fixed O, and actually this is your vector OA, right, the vector A. Now, look at the same line in the other direction, right. Now, we'll call this as A prime for a moment, right. So, how do you get A prime? On the straight line OA, on the other side, same distance. That is, in other words, O is the midpoint of A prime A. Or, right. Now A prime is a vector, isn't it?
Yeah, OA prime.
Now, A prime is a vector, OA prime. Right. Now, right. So this is the vector A. Now, the point A prime or the vector A prime is as described in the diagram. Right. How do you get it? On the line OA on the other side. Now I am going to look at the vector A plus A prime. By definition, what should I do? How do I add two vectors? First I have to look at the midpoint of the line segment. So I have to look at the midpoint of A prime A. What is the midpoint of A prime A? O. What is the reflection of O about O? If an image is on the mirror itself, then is its image. See, I stand on before the mirror. Say the mirror is 2 feet or say 30 centimeters. I am 30 centimeters in front of a mirror. Where is my image? 30 centimeters behind, isn't it? Behind. Now, if I am 10 centimeters from the mirror,
10 centimeters.
If I am exactly on the mirror,
no image.
Image is there, but coincident. So image is the same as the same. So right. So the reflection of O about O is itself. Right. So how do I add A and A prime? A and B, look at the midpoint. That is O. and reflect O about this. O about O is O.
Oh.
Right? That means A plus A prime is O.
Oh.
Right? That is, I have given any vector A, I have found another vector A prime, so that the sum is the zero vector.
Zero.
Right? So A prime is denoted by minus A. Right? So if OA is one vector, so where is minus A? Given a vector A, where is minus A? So join O, join to O, then produce it. So this is A, this is minus A. So you just have to reflect A about O. Right? Geometrically. Reflect A about O, that you get minus A. So the vectors and their addition have all these nice properties. You can add any two vectors. Addition is commutative, addition is associative. You have a nice zero vector, and every vector has a inverse vector, so that the sum is the zero vector. You see that this seemingly simple comparison and verification that vectors and their addition also have these nice properties helps you to solve many of the problems that see, many of the things. First of all, it explains many things that happen around us. So let me ask you a very simple thing. Okay, I have some big weight, say an iron ball or an iron box. Right? I have an iron box. And what we are going to do is, see, let me read, right? So this is my iron box. I am pushing it in this direction. Right? Imagine that there is no friction. Right? Then what will happen to this? This will start moving in this direction. So when I push it, it moves in this direction. Right? Suppose I don't want it to move. Right? So you try to push it in the opposite direction. Alright? Now, if I apply a force F1, what should be the force F2 that you should apply so that it doesn't move? In magnitude must be the same, isn't it?
Yeah.
Only it must be in the opposite direction. So if the two forces are in the same line, the magnitude of force F1 is balanced by a force of a magnitude of force same magnitude but in the opposite direction. Then they are force, correct? So something towards east if I push, and then towards west somebody should push with the same force, then there won't be any movement. Suppose F1 is bigger than F2, right? So this F2 is this way, F1 is bigger than F2, then what will happen?
Motion continues.
It will move in this direction.
Yeah.
And the effective force in that will be F1 minus F2, isn't it? That's what is in the magnitude, right? And that is exactly what you are seeing here. Now each force, so I say direction and magnitude. The force is a vector, right? Now I have a force, so this force is a vector, this force, so I have to balance it by another vector, another force. So with force F, I have to balance it with minus F. F is a vector, A is a vector, minus A is a vector. Right? But imagine that, say here, this represents U. Right? You may be wondering, see, I am a three-dimensional body, you are just representing it by a point. So this is just a representation, assuming that you have no other dimension, right? Just a point. And you are replaced by a point. Maybe you can, if you want, you can. What is, say, when you are acted on by, say, when I stand, how do I stand? Why do I stand? How do I stand? I don't move. See, what are the forces acting on me? Gravitation force, right? That is pulling me down. Okay. So, that is, and when am I stable? Right? See, for example, so I'm just a bit funny, right? So, this is the face. Right, and suppose somebody right? A very bad, fat belly or something, right? Now, if he tries to bend forward, what will happen? Or usually I ask this example to my students. Say, school days, there is an annual sports meet, right? And the sports meet, usually there is an old boys race, and then there is another race among the staff members, right? Race among the staff members. And among the staff, there are staff between 20 and 30, 30 and 40, 40 and 50. So there will be, nobody will group for say, 20 and 30 with the person above 50. So there will be a race for a middle aged or say above 50 or above 45. And if you observe carefully, say, if for the others, if it is one full round of the ground, say 400 meters, for about 20 and 30, maybe 200 meters, for 30, for 40, maybe less, or for above 50, maybe still less, 50 or 100 meters. Then two people stand with a rope or a small thread and they finish here, the finishing line. But invariably, for the elders, when they come to that rope, most of them will fall or will try to fall. What is it? What is the reason? What is the reason? The reason is, see, when you run, right? When you are running, you are bending towards the front, right? And then each point, say each body has a center of gravity, right? And made of several particles. Each particle has each particle is pulled so as a weight, right? Now all these I will assume that they are all, because the center of the earth is far away, so we can assume they are all parallel. They are vertically down. They are all parallel. So if I apply, so they are all forces or vectors in the same direction. Adding two vectors in the same direction is very simple, no? So if I want to add two vectors in the same direction, I just have to add the magnitude. Right? So each particle has a weight. So what is my total weight? The sum of all this. But then I am replacing that by a single point. Say the total weight. Now all these, suppose I have a big rod, right? A rod, a pole, which has no weight. It's ideal, right? Something in reality you cannot have, but imagine that you have a pole or a rod which has no weight, right? I carry, here a big bucket of water, a drum of water, a bucket of water, right? And then I carry half this size here, full of water. With some scaling, this is 2, this is 1. That is, this is double the size. Yeah. Okay. Now, where will you support? Where will you have this? Say you want to support it on your shoulder. Where will you support it?
0:1 to the biggest.
If they are the same weight made in the middle.
Yeah.
So will it be near here or near here?
Near the bigger one.
Near the bigger one?
Yeah.
Okay. Near the bigger one you support it. Now, why is it that that is because these two forces are, when you support it, you are giving a force in the opposite direction, isn't it? These two are vertically downwards, and then you are giving, we feel a reaction here, we are giving a vertically upwards, equal to W1 plus W2, 2 plus 1, right here, 3 upwards. But that cannot be here or here. That has to be at precisely one point. That you call the center. That's where the resultant acts. Right? That point. Okay. Similarly, all my parallel forces, right? They will be replaced by one resultant acting at one point. That you call the center of gravity of the body. Right? So, right. I will have a center of gravity. And this man has a center of gravity not somewhere here but somewhere here.
Yeah.
Right? Because this is where his center of gravity is. So now the weight, his total weight is acting at this and it is pulling him down. So what will happen? He tries to fall to the front. Right? But for a normal person, if I want to stand stable, my stability will depend on whether my center of gravity falls within the base. Within the base. Right? If I have a big irregular solid and then if the center, say with this base, some big solid is there. If the center of gravity, very irregular, right? On this platform, an irregular ball, big weight is there. If the center of gravity is somewhere here, it will be highly unstable immediately, right? But if the center of gravity is somewhere here within the base, then it won't be. So because slightest disturbance here, it will topple it. Right? So you see that the usually a general problem in practice is several forces act at a point, whether it be in physics or engineering. See, this is essence of that. See, if you replace a body by a particle, right, and you several forces acting at a point. Now the question is, you may be knowing, say, this is your P, and several forces are acting. Now you want to know what is the net effect of all these forces. Right? So net effect of all these forces. Does it keep the particle in equilibrium, or does it move the particle, or what is the effect on that particle? Right? See, look at ourselves. We are now acted on by gravity, force due to wind, force due to air, so many things. But most of the things are negligible with respect to this, so we look at only. Right? Now, in a typical problem will be, suppose 10 forces are acting at P, and you know that the point P is in equilibrium, that it doesn't move. Right? And of these 10 forces, 9 are known forces. 9 forces are known forces. Now the problem is to find the 10th force. How will you find it? That is where this comes. Because if you, these are forces are vectors. Right? So I will have F1 is a vector, F2 is a vector, F9 is a vector. So these are the 9 known forces. Right? Plus an unknown force X is 0. Right? They keep it in equilibrium. So these forces, the net effect is 0. 10 forces, these 9 forces you know, only this you do not know. Now do you know how to add two vectors? Yes.
Magnitude, add the magnitude.
Magnitude and also the direction correspondingly here. See, just now you learned that now this force, this is one force, this is another force.
And find a midpoint.
Right. So then this is your F1 plus F2. Right? Either you complete the parallelogram or look at the reflection. So you know how to add two forces. So because of associativity, you know how to add three forces, you know. And therefore 4,
Therefore, yeah.
5, and therefore n number n. So you can add these 9 forces. That will be a single force F. Right? Adding n vectors. Plus x equal to 0. So what is this? X must be equal to minus f. With every x you have a minus. So you have found out the resultant. Right? And you have found the what should balance. Right? And this is a typical problem in because you want the particle in equilibrium. So what are the other words to say it doesn't move? Something. Can you give me another English word that it doesn't move? Stable, or it is fixed. It is fixed on one word. It is, and then fill it up by something. Rooted, fixed. Yes. Some more. Starting with yes.
Static.
Right? And study of static mechanics. Right? Particles in equilibrium, but bodies in equilibrium, that is statics. Right? And study of bodies which can move, and that is dynamics. And if you study particles in motion, is particle dynamics. And then you have bodies, but then when your bodies move, see, it's not just mathematics, something physics is also involved. See, the body is composed of matter, and then how they are trapped, how it is densely packed, and then their deformities and other things, so many other things. But if you replace a body by a particle, then you can use these vectors. Velocity is going to be a vector, right? And acceleration is going to be a vector. So, in some sense, So now today, see, you have learned vectors in a slightly different way. In the geometric scene, see how the vectors are translations, and a translation is fixed by a point and its image. So I fix a point O, so in the plane, so each translation will be fixed by the image of O, so A, so each translation is denoted by a point A in the plane, so different points in the plane, different vectors. So vectors in the plane can be replaced by points in the plane. Then we define a ray of adding 2 points, or this adding 2 vectors. Adding 2 points, how do I do that? A and B join A, B, look at the midpoint M. I have fixed a special point O, reflect O about M, I get this, and then you see this you define as A plus B. Right? Then we saw that vector addition is a commutative, associative. We have the zero vector and then every vector as an additive inverse, and therefore algebraically this vectors together with this addition behaves very similarly like the integers and addition. Right? And one nice application of this is stereostatics. Right? In the study of static forces acting at a particle, this has a nice application. Yeah, there are several good problems. So next, see, we will learn. Now, see, once you understand the object that we are handling, then can slowly increase our speed. Right? So initially, it is static.
Then
Right? First, we start about just a vector, stay there and then learn. Then from statics, slowly there is a constant vector, right? It's a uniform motion, right? And now the velocity is also we are going to increase it, so there will be acceleration, right? So next we will see that there will be some acceleration, and these velocities, acceleration, and how to, so vectors, our study of vectors will be accelerated in our next.
Thank you.